Hello everyone. In this video, I will briefly discuss how to design a vibration isolator when the primary system is forced at its own natural frequency. Starting with a single degree of freedom system, so let's assume that I have a one mass, one spring system when the dashpad or the damping is neglected. So the system is subjected to some force f of t here, and I have a sliding card M1 and which is attached to a spring K1. Assume that I'm able to read either the position, velocity, or acceleration. To get to the equation of motion, because I have a 1 degree of freedom system, I have to draw a free body diagram. From here, if you move the card to the right by x, there is one opposing force from the spring, which is by K1 times x of t. We have an excitation force F of t. And if you set the equations of motion using Newton's laws of second law of motion, I have total force which is equal to mass times acceleration. Because to the right is assumed to be positive in my sketch, so the spring force is negative. Then we have a positive external force which is equal to mass 1 times acceleration. So I can actually correct this. This is acceleration 1. Okay. From here, the equation of motion of the single degree of freedom system becomes mass 1 times acceleration 1 multiplied by k1 plus x1, which is equal to the force. So that the natural frequency of the system, please remember how we found the natural frequency. If you're interested in natural frequency of the system, you should disregard the force. Because when a force is applied to a vibratory system, the system starts oscillating at the forcing frequency. If you're interested in finding the natural frequency of the system, this must be an free response or an unforced system. However, I have a force, which means the system is no longer oscillating at its own frequency. It will be oscillating at the force frequency. The natural frequency of the system is square root of k1 over m1 in radian per second, and in hertz it should be 2 pi times fn1. Assume that this force, implemented force, okay, is equal to 8 times sine omega t. So you can select the step signal, you can select the harmonic signal, you can select a ramp signal, but let's say your force is harmonic. You're applying a harmonic force to the system. So that A is the amplitude, magnitude of the force, and omega is you can call this either as forcing frequency or excitation frequency. If somehow this omega, this forcing frequency, becomes the natural frequency of the system or is equal to the natural frequency of the system, please remember we call this phenomena as resonance, so we will expect large amplitude of oscillations. Most of the systems, we are not going to break it because systems, mechanisms, or the machines are maybe mechanically limited. There are some mechanical constraints in the system, or there is damping that really prevents the system to break. My question today is, how can we control the vibrations when the system is forced at its own natural frequency? Is there any way I can design a passive passive vibration isolator so that even if I'm still exerting the system by this f of t, when this forcing frequency is equal to the natural frequency, the oscillations, the amplitude of oscillations will be damped. I will expect really large amplitudes of oscillations when omega is equal to omega 1. However, I'm trying to design a vibration isolator, and we are going to call this passive vibration isolator, by adding a secondary system to my primary system. So let's see this sketch. I have a spring. Still, this is my first system, primary system. We have a spring, we have a mass, and I'm able to read the position, velocity, or acceleration, and the force is only implemented on the primary system. Now, I'm interested in designing this vibration isolator by adding a spring and a mass system. So we are going to call this our vibration isolator or secondary system. This is a 2 degree of freedom system, translation of 2 degree of freedom system, so I can write the equations using this matrix method. So you have a mass matrix multiplied by acceleration plus stiffness matrix multiplied by displacement, which gives you the forces. Remember, mass matrix is always diagonal. Then, looking at the first element, I'm focusing on this first card. We have two springs attached. That's why this will become K1 plus K2. If you're only looking at the second card, there is only one spring attached to the second card. That's why this is positive K2. Whatever in between, I have only one spring between mass 1 and mass 2. That's why these two becomes negative. If you don't know how to set the equations in mass matrix form, please just draw a free body diagram of mass 1 and mass 2 separately, and after that indicate the forces acting on each card. After this, please set the equations for total force equal to mass 1 times acceleration 1 and total force is equal to mass 2 times acceleration 2. After that, you will be able to write the equation of motion. So using one row, one column, I have mass 1 times acceleration 1 plus K1 plus K2 times x1 minus K2 times x2 as equal to the force. After this, we have mass 2 times acceleration 2 minus K2 times x1 plus K2 times x2 as equal to 0. Let's say the cards are oscillating at, remember please, for forced systems, we are no longer having a free response system. For forced systems, both cards will be oscillating at the forcing frequency. Remember how we defined force frequency is in the form of A times sine omega t. So this omega is my forcing frequency. In the most general case, let's assume, just omega. Omega is not equal to omega 1, but I'm solving the equations for any forcing frequency. Let's say the position of the first card is x1, which is the amplitude of oscillations, multiplied by cosine omega t plus phi, and xt is equal to this position of the card is equal to another amplitude multiplied by cosine omega t plus phi. If you take the first and the second derivative of both x1 and x2, you will get to these equations 2 and 3, which means acceleration and position of the cards are directly proportional. So we just found a linear relation between acceleration and position in the frequency domain. Similar to the second acceleration, I have x2 double dot, which is equal to negative omega squared times x2. Remember, omega is our forcing frequency. If equations 2 and 3 are plugged into this equation number 1, we are gonna get, if you plug those in and factor out by x1, x2, I will get to this form. And from here, I can easily write the equations as k1 plus k2 minus omega m1 times omega squared as x1 times x1 minus k2 times x2 as equal to the force. And the second equation of motion becomes negative k2 times x1 plus k2 minus omega m2 times omega squared times x2 as equal to 0. Remember, omega is the forcing frequency. So my question to you, how can we find x1 and x2? Going back to MATLAB from here, let's write the equations, but I have to use symbolic toolbox. So from here, I'm going to define using sims, I will define the symbolic variables. So I have to define m1, m2, k1, k2, omega, x1, x2, and f. After this, let's write the first equation. Equation number 1, remember it was equal to, let me get to the equation, it was k1 plus k2. This all comes from, this is the first, first row, first column. I have k1 plus k2 minus m1 times omega squared multiplied by x1. Then we have minus k2 times x2 minus f. So whenever you define a function equation in MATLAB, make sure that the right side of the equation becomes a 0. Then what I should do is I have to define the second equation. The second equation is, going back to this, I have negative k2. We have negative k2 times x1 plus k2 minus m2 times omega squared times x2 as equal to 0. So this equation is already set to 0. After this, I'm trying to write the equations only for x1 and x2. Using the second equation, because the right side was 0 and doesn't involve any f term, so I can define x2 in terms of x1. So what I will do is I'm going to solve equation number 2. To make this first, I'm going to make this equal to 0 and solve for x2. So this x2 is written only in terms of x1. This helped me to define x2 in terms of x1. After this, I can define another equation 1. I will say this is equation 1d. What I will do here, now knowing that x2 in terms of x1, I will just plug in wherever I see x2, this x1. So I will substitute in equation 1, wherever we see x2, we are going to plug in this value. Okay, this function in here. If you do that, this equation will be only simplified into x1. From here, after this, I can just solve equation number 1d. I'm going to make this equal to 0 and only solve for x1. So this gives you another function. If you want to plot this in a pretty form, just write pretty answer. And MATLAB just plot the answer in a different way. If you make the common denominator, so you multiply these two functions, you expand the first fraction by this k2 minus m2 times omega 2 squared, and then flip it, so this will yield into this equation here. x1t will be f times k2 minus m2 times omega squared over k1 plus k2 minus m1 times omega squared. Remember, I multiplied this denominator with the numerator, so you get to this form, minus k2 squared, but if you flip the denominator, so it will be the product on the numerator. If you follow the same procedure, and let's say this time you solve equation number 2 this time, I'm sorry 2, but let's say you want to solve it for x1. Okay, this is now our x1. So in equation 1d, this time I want to plug in wherever I see x1. I'm going to change the equation. Wherever we see x1, we are writing this in terms of x2 now. I'm going to just copy and paste this. Okay, and then we will solve, okay, after this we will solve this equation number 1, new 1d, and I want to solve this for x2. So this will be my new equation, and if you want to just plot this in a pretty form, this gives you exactly the same answer. So this is going to be actually f times k2. You can flip this and expand this k2 by k2, so this is going to be k2 squared. And there's a negative sign, you can distribute it to the denominator if you want. So I just wanted to show you can still solve this problem by hand, but this is how I solve in MATLAB. After this, okay, once you know x1 and x2, and going back to our question, so my goal was, I was trying to design a vibration isolator. So from here, what I'm trying to do simply is I'm trying to dampen the oscillations of the first card to make x1 equal to 0 if possible, or as small as possible. Okay, so x1t, so I'm only interested in x1. My goal was to just dampen the oscillations on the primary card. So from here I will set this equation equal to 0 first. But then mathematically what that means is I want to make the numerator 0, so that f times k2 minus m2 times omega squared must be equal to 0. Since force cannot be 0, remember force was a times cosine omega t or sine omega t, really doesn't matter. I don't want the force to be 0. This is going to be a force system, so that k2 minus m2 times omega squared must be 0, so that we're going to get omega squared as equal to k2 over m2. So I have to just restart my notes. It's kind of frozen. Let me first deal with that. Okay, now it's going to help. Going back to good notes and opening this vibration isolator. Perfect. continuing from here, if omega squared is equal to k2 over m2, then omega, remember what our omega was? We want to, if you remember from our first slide, we want to excite this system. I want to excite this system f of t, okay? So that this forcing frequency becomes the natural frequency of the first system. And natural frequency of the first system was equal to square root of k1 over m1. Knowing the relations then, if omega is equal to square root of k2 over omega 2, and remember this omega was equal to omega 1, which means this is the worst case scenario, which means the primary system is subjected or forced at its own natural frequency. So omega will be equal to square root of k1 over m1. This is wrong, let me correct that. And then remember, omega will be also equal to square root of k2 over m2. If you make these two equations equal to each other, this gives you a ratio, so that k1 over m1 will be equal to k2 over m2. But there's a limitation. If you are designing a secondary system, when the primary system is subjected or forced at its own natural frequency, your design vibration isolator must satisfy this equation. K1 over m1 must be equal to k1 over m2. However, k1 must be greater than k2 and m1 must be greater than m2, which means your primary system has a larger mass and a stiffer spring. Then it's expected that the oscillations on the primary part will be significantly damped. Going back to this sketch again, I just want to give you an example. Please do not use my parameters. I've designed a system. K1 is 600 Newton per meter, mass 1 is 2 kilogram, and the natural frequency is equal to, so if you calculate the natural frequency of this primary system, it's 17.32 radian per second. While designing the secondary system based on what M1 and K1 are, so K1 over M1, okay, is equal to 600 over 2, which is 300, so that I should have a ratio of K2 to M2 equal to 300. So that I selected K2 to be 300 and M1 to be 1 kilogram.